This example looks pretty ugly for us to be able to find the derivative of. And it actually is a fairly difficult problem unless you remember that there are certain properties of logarithms that can help. And in fact, there's two properties that are going to make this problem a lot easier. Now, we're not doing any calculus yet. We're just using the rules of logarithms. Remember, we have two rules. We have log of mn equals log m plus log n. And then another rule that we have is log m over n is equal to log m minus log n. And we're actually going to use both of those rules because we have a product in the numerator, but we also have a quotient, obviously. So another way to rewrite this by using some logarithmic algebra is ln of 2x plus 9 plus log of x plus 1 to the 6th minus ln of 1 minus 5x to the 5th power. Now, that's not the only rule that we can use, because you might remember that there's also that exponent rule for logarithms, meaning that if you have an exponent attached to a logarithm or a factor in there, then what you could do is you could just move the exponent as a coefficient. So another way to write that is ln 2x plus 9 plus 6 ln x plus 1 minus 5 ln 1 minus 5x. And now we're ready to find the derivative term by term, which is going to be much easier for us than being able to go through and trying to find the derivative using a quotient rule, a chain rule, a product rule, all the different rules we would need to do this one interior. So here's our derivative. So let's just go term by term. The first one is 1 over 2x plus 9, but then we have to multiply by the derivative of 2x plus 9. We have our second term. We're going to have 6 times 1 over x plus 1, and then we're going to have to multiply the derivative of x plus 1, again, our chain rule. And then finally, we have that minus 5 ln of 1 minus 5x, so that's minus 5, 1 over 1 minus 5x, and then we're going to multiply by the derivative of 1 minus 5x. We know the derivative of 2x minus 9 is 2. We know the derivative of x plus 1 is 1. We know the derivative of 1 minus 5x is negative 5. And what we could do is we could just multiply each of the coefficients, either in the numerator or out front, by whatever's in the denominator, or whatever the derivative is, excuse me. So our final answer for this, 2 over 2x plus 9 plus 6 over x plus 1. And then we have negative and negative, which is going to turn into a positive. And then that just is going to turn into 25 over 1 minus 5x. And that's going to be our final answer for that derivative. All right, much easier again than trying to use all the rules on this thing. Another example of being able to work with this. So this one is just a straight quotient rule. All right, there's nothing we can do to simplify this. So I don't want you thinking that we can always use the rules of logarithms to simplify. Right, so just to remind you about our quotient rule, f over g prime is equal to f prime g minus f g prime divided by g squared. Right? And so in this case, f is going to be ln x, and then g is going to be ln x plus 4. And the good news is for both of these, what we're going to do is we're just going to take the derivatives, and they're both going to be 1 over x. Right? So for f prime, it's 1 over x, and for g prime, that's 1 over x. And we could do some fancy algebra at the end. And so here's our solution for this. So our derivative is going to be equal to f prime g. So that's going to be 1 over x, quantity, ln x plus 4, minus fg prime, which is 1 over x times ln x. And then in the denominator, we're going to have ln x plus 4 quantity squared. All right, now, here's where it gets a little bit ugly because we are going to have to simplify this, but it's not too bad because notice that we have a common 1 over x, so we can factor that out. And so we can rewrite this as, I'm just going to pull out the 1 over x and I'm going to put it out front. So now what we're left with is ln x plus 4 minus ln x. And then in the denominator, we have ln x plus 4 squared. Right? So again, all we did was we just factored that 1 over x out. And notice really nicely in the numerator, those ln x's are going to cancel each other out. Really nice. And then finally, we can just write this as our final answer. So we're going to have 4 over x ln x plus 4 squared. All right, so nice and easy on that derivative, not too bad. All right. Finally, this is a technique that we're going to use to be able to find the derivatives of anything that has an x as an exponent. All right, so if you have x as an exponent, or a term that contains x as an exponent, you're going to use this technique called logarithmic differentiation. And I'm going to illustrate this technique just because this is a really easy example of how to do this one, because it's only 13 to the x. But let me illustrate the technique for this. So what we're going to do first is we're going to take the natural log of both sides. And you might be thinking, well, I don't want to introduce a logarithm because that makes things even more difficult. Right? But the good news is that, remember, we have that rule with exponents and logarithms to where we can move the exponent as a coefficient. So we can rewrite this as ln y is equal to x ln of 13. All right? So step 1 for logarithmic differentiation is to introduce a log and then remove any x's in the exponents. So we're going to use that exponent rule. Okay. Now we're going to take the derivative of both sides. This is actually a fairly easy derivative. The log of y is 1 over y. But remember, whenever you take the derivative of a y, we're going to have dy dx. On the right-hand side, ln of 13 is just a constant. So we don't even worry about that. The derivative of x is 1, so we just wind up with ln of 13. Right? After we take the derivative, the last thing we do is we solve for dy dx. Right? So to do that, we're just going to multiply both sides by y. So we're going to get dy dx is going to be equal to y ln of 13. And you might remember all the way back at the beginning of the problem, remember y was equal to 13 to the x. So what we're going to do is we're going to substitute 13 to the x back into this answer to get the function completely in terms of x. All right, so our final answer for this is going to be dy dx is going to be equal to, instead of y, 13 to the x natural log of 13. Right? So that's our technique for logarithmic differentiation. Now, in the last two examples that I'm going to show in the next video, the examples are going to be more rigorous. All right, but this is just a really easy example for logarithmic differentiation. And when I say that, I mean with respect, because none of them are really all that easy. So in the next two videos, we're going to ramp up the intensity a little bit with these, introduce one of those tangent line problems, and then show a little bit more rigorous algebra with those.